Step 19, I can solve and graph exponential functions. An exponential function is a bit different than any of the functions we've been working on this year. It's where the variable is in the position of the exponent. Now, what would this look like in real life? Well, occasionally things grow at a steady rate, and sometimes things grow exponentially. Money can grow exponentially. Kind of think back to that old riddle. Would you rather get $1 million at the end of a month or get 1 penny on the first day and then double it on the second day and double it on the third day? That is an example of an exponential growth because it's doubling every day. It's not just adding 3 pennies a day. That would be a linear change. It's exponential. Or think about videos on social media that go viral. It's because the video is first shared with 100 people, and then those 100 people share it with 100 people, and so on. And before you know it, it's got millions of views. That's an example of an exponential situation. The parent function that we're going to be studying is y equals b to the x, or f of x equals b to the x, where b, the base, is bigger than 1. It's not a fraction. If it is a fraction, that's going to cause exponential decay, which we will get to in a little bit. The domain is going to be all real numbers. For the parent function, the range is where y is greater than 0, because there's no value of y when y is negative. Let's practice graphing. To graph y equals 3 to the x, we're simply going to go to Desmos, and we're going to type in y equals 3 caret x. And there's a picture of our graph. That's what we want to get onto our page. To do that, we're going to press the gear button. We're going to press the table, and we get a nice list of nice little points that we can plot. So we can plot the point 2, 9. We can plot the point 1, 3. We can plot the point 0, 1. Just working my way up the list. -1, 1/3 is harder to plot, but it would be about there. -2, 1/9. It's getting harder and harder to plot. But now you can see that when I try to connect these points, start here and work to the left actually. You're approaching 0, but we never cross 0. 0 is our asymptote. All right, let's talk about the domain and the range. The domain, I'm going to look at the x-axis. There is graph above the x-axis everywhere I highlight. It looks like it kind of stops here, but remember that arrow goes on forever, so I have to assume it just keeps getting further and further and further to the right. So my domain is going to be all real numbers, from negative infinity to positive infinity. The range, there's no graph down here until I get to 0. Then there's graph either to the left or to the right all the way up. So my range is going to be from 0 to infinity. We can also do transformations of exponential functions just like we transformed radical functions, just like we transformed rational functions, and the rules are going to be very similar. If we start out with our parent function, y equals b to the x. In fact, I'll even give you a concrete example. Let's use y equals 3 to the x, the last example we just had. If I add a number outside the function here, like 7, that's a vertical translation. It's going to go up if you add a number or down if you subtract a number. What would that look like on our graph here? Well, if I select my graph, if I add 4, that means this point right here is going to go up 4 spots. It would make it go up 4. Now, how do we make it go left and right? Well, if we add or subtract a number up here with the x, like maybe minus 2. That's going to make it go right 2. And if I add 2, it would go left 2. So the number with the x, remember it's kind of the opposite of what you'd think. If we add a number to x, it's going to go left. And if we subtract a number, it's going to go right. Similarly, if we put a minus before the function, it's going to make it reflect over x. If we squeeze a little number in here, let's see if we can't do that. There's our parent function. If I were to multiply by a number before it, that's going to make it stretch vertically. Unless this number that I put in here is a fraction, now it's going to have a vertical compression. Let's practice. So here our parent function is y equals 2 to the x. How are these different? Well, we've added 1 outside the function. This causes a vertical shift up 1. So when I graph it, I'm going to use my graphing calculator this time. I'm going to type in y equals 2 caret x plus 1. I'm going to look at the graph. To get this graph onto my paper graph, I need to look at my table of values. And I have a lot of nice points that I can plot. I can plot the point 3, 9, 2, 5, 1, 3, 0, 2, negative 1, 1 and a half, negative 1, 1 and a, negative 2, 1 and a fourth. And these numbers keep getting smaller and smaller, but they never get to 1. See how they just keep getting really, really close? I mean, it says 1 right there, but that's because the calculator is rounding, but it never drops below that because 1 is our asymptote. So we are going to start here and get lower and lower and lower and approach 1, but we never cross 1. It is our asymptote. Let's talk about the domain and the range. The domain is still all real numbers from left to right. My range has changed a little bit. Before it went from 0 to infinity. Still goes to infinity. But it doesn't go down as low as 0 now. It stops at 1, the new asymptote, because it's shifted up 1. We won't graph this one, but let's address all of the little changes that happened here. We are subtracting a number from x. That's going to cause a horizontal shift. Opposite of what you'd think. It goes right 2. We also have something else happening here. We have a negative sign out front. What does that do? That's going to make it reflect over the x-axis. And then finally, we have this 1/2 out front. What does that do? That's a vertical compression. Remember, our parent function would have been y equals 5 to the x. Y equals b, the base is 5, to the x. So what did I do to this? I subtracted 2 in the exponent, and I put a negative 1/2 in front. Causes all of these changes. Again, if you type this into your calculator, get a table of values, you could plot that. Sometimes we are doing real-world problems where they give us a rate. And if the rate is causing an increase, we take that percentage and we add it to 1, And this is our base, and that's our growth factor. In this formula, this is going to be the ending amount, and this number right out front is going to be our initial amount. So if we're talking about money, this is the money you start with. If we're talking about number of cells, this is the number of cells you start with. If we're talking about a population, this is the initial population. This number right out here, T, represents our time. And R, again, is the rate, often the percentage. Okay? In this next example with population, the first U.S. Census was conducted in 1790. At that time, the population was, that's key here, the population was 3,929,214. That's what it started at the first time we did the census. Since then, it has grown by approximately 2.03%. That's our rate. And it's growing, which means we want to add that to 1 to show growth. You can't multiply something by a number smaller than 1 and expect it to grow. So we want to first come up with an equation that would model this scenario. So our equation, if we go back to, we have A of t, I'm just going to call that y because it's function notation. A, 1 plus r to the t. But we can fill some of these things in. We know the rate that it's growing. We know the initial amount. So when we replace these things, y equals 3,929,214. 1 plus the rate. Now, when we put this in, we don't want to use the percent symbol, so we need to convert it to a decimal, which would be 0.0203. Because you move your decimal 2 places to the left to convert it. 0.0203 to the t. And the only thing left that we could do to tidy this up, we can simplify our parentheses a bit and call this 1.0203. Takes out that plus sign because 1 plus this decimal is 1.0203. If I were to graph this, we would have 3,929,214 parentheses 1.0203 close parentheses to the x equals y. Now, when I look at this on my graph, I can't find it because I'm only looking at a tiny window. I need to kind of zoom out, see if we can't find this graph. Oh, there it is. Way over here. That's what the graph is looking like. There we have it. Now, occasionally that graph is challenging to view in Desmos, so let's take a look at what that would be in our TI calculator. If we go into our graphing calculator and we type 3,929,214, parentheses 1.0203 to the x. And we're going to set our window. It's a good example of practicing the window. X, or t, represents time. Time can't be negative here, so the time starts at 0. 1790, how many years ago was that? Well, 2020 take away 1790 would be approximately 230 years. So let's play it safe. Let's call it 250, just so that we can capture enough graph. And our y value, population, well, the population is never zero or below 0. So we'll start it at 0. And we know that if we go up to 4 million, that should be enough. So there's 4 million. And now when I look at the graph, oh, it's not showing up. Because I forgot to adjust my scale, I'm going to count by 25s for my X scale, and my Y scale, I'm going to count by 440 million, actually. 1, 2, 3, lots of zeros to keep track of. I believe my Y max is too small as well, so we're going to put some zeros on the end of that. Now let's try to graph. There it is. Now we can see our graph. All right, let's take a look at another problem. We're just going to set this one up. We're not going to graph it. Teen spending is expected to grow, so we're going to start with our original formula, 1 plus the rate. It's expected to grow 3.5%. That's going to be our rate. We know it's growing from this amount. So that's our initial amount. So we're going to say y equals 208.7 billion. 1. Now I'm going to add this in the same step. 3.5% as a decimal looks like that. So 1 plus that is 1.035 to the t. And if we wanted to know what the teen spending is expected to be when it's 2020, let's write that out. What is teen spending projected to be? In 2020. Well, that is all about time, but I need to know what to put into my formula here. Y equals 208.7, 1.035, but do I put 2020 right here? No. How many years have passed if it's 2020 from 2012? Well, that would be an 8. And then we'll type that onto our calculator. We'll type in 208.7 parentheses 1.035 to the 8th. That means they're projecting the spending to be $274.8 billion. All right, as promised, let's talk a little bit about exponential decay. Decay is the same thing as our exponential growth, except now our base is always going to be a fraction, like 1/3. Just looking at this function right away, I know it's not growth, I know it's decay. And we're going to treat it the very same way. We're just going to go and type this into our calculator, y equals 1/3 to the x. Go back to the home button. There's our graph. If I want a table of values, I just grab it by touching the gear shift, and I can plot all of these points. I can plot the point -2, 9, -1, 3, 0, 1, 1, 1/3, and so on. And again, I still have that asymptote. It's getting closer and closer to 0, but it's never crossing. When we talk about the domain, we're going from -infinity to infinity still. And the range is still from 0 to infinity. But with growth, the function from left to right looks like this. With decay, it starts out big as you go from left to right and gets smaller. Okay, what transformations have happened here? Lots of things happening. We've got this factor of 2. 1/4 is just our base. We've got this factor of +2. We have -3. What do all of these things do? Well, this is our vertical stretch by a factor of 2. Adding 2 to the x makes it go left 2. And subtracting a number outside this function makes it go down 3. Those are the 3 transformations that are happening. And again, if we have a growth factor, we can also have a decay factor. If you multiply repeatedly by something smaller than 1, and I know this is going to be smaller than 1 because if I take 1 and take away the rate, it's lower than 1. Like in this example here, we have a cup of green tea. Start with our original function. Oops. Now we're decaying, so it's going to subtract the rate. We are starting with 35 milligrams. That's our initial amount. And then we're going to take away, eliminate some of that caffeine. That's our rate. So first, let's write the function. We start with 35. 1 minus, what is this as a decimal? 0.125. To the t. And then we could simplify what's in the parentheses here. Y equals 35, 0.875 to the t. Then it says, estimate the amount of caffeine in a teenager's body 3 hours after drinking a cup of tea. Notice that this is caffeine from their system per hour, so I know T represents hours. So if I want to figure this out, all I have to do is put 0.875, and I'm going to put a 3 for my time. Let's clear out my calculator. So 35 parentheses 0.875 to the third tells me that after 3 hours, there will be approximately 23.44 grams of caffeine left. 23.44 milligrams left. And I didn't put in equals because I rounded, so I changed it to a squiggly equals.